Introducing myself, Shalu MS from Department of Mechanical Engineering. My hearty welcome to everyone present for the online ATAL-FDP on Green Energy Solutions, Building a Sustainable Carbon Neutral World, organized by Department of Mechanical Engineering, College of Engineering, Kottayam. For the second session today, for the topic Acoustic Energy Harvesting, we have Dr. Minu A. Pillai. Dr. Minu A. Pillai is working as Assistant Professor in Department of Electronics and Communication Engineering, Indian Institute of Information Technology, Kottayam, since 2022. Her research area include acoustic energy harvesting, piezoelectric energy harvesting, and acoustic source localization using machine learning. I kindly invite Dr. Minu A. Pillai on board.
Good evening, everyone. It is a pleasure to be here with all of you in this faculty development program on green energy solutions, building a sustainable and carbon neutral world, organized by the Department of Mechanical Engineering by College of Engineering, Kottayam. Sir, I'll share my PPT. I'm Dr. Minu Pillai. I'm working as Assistant Professor in the Department of Electronics and Communication Engineering of IIIT Kottayam. Before coming to the topic of acoustic energy harvesting, I'll just tell something related to the power which we need for various applications, especially the applications which are related with IoT devices. I don't know, like whether most of them will be belonging to mechanical department or not. Sir, what about the audience? Whether they are all from mechanical background?
No, teacher, interdisciplinary background.
Okay, fine. So some of you might be, even mechanical students might be knowing about IoT related areas because this is a booming area in nowadays. So today, actually, we are facing an exciting challenge. Like how do we power the billions of IoT devices that are transforming our world without burdening the environment with an ever-growing need for batteries or solar panels? Okay, so that is the biggest challenge. You know that these IoT devices, like as smart cities, remote environments, and wearable devices, they continues to evolve, and we can see there are a lot of articles related to this in most of the technical journals and magazines. There are so many articles related to this. If you are seeing such contents, if we can see that a massive increase is there in the number of IoT devices. Okay, so whatever is there in this PPT has been taken from one article, which is based on this number of IoT connections worldwide 2022-23. It's a very famous article related to this IoT. So it's telling that by 2030, around 50 billions of these IoT devices are expected to be in use. So you know that these IoT devices are mostly reliable on these sensors, right? And how do we power these sensors? How do we do we have enough power to power these sensors? That is a big question. Okay, major concern actually. And these devices, most of the devices are actually revolutionizing everything from healthcare to some urban planning. Okay, but the major concern there also is how do we power them sustainably, without any interruption. That means any interruption means without consistently changing the batteries. You know that batteries, if we are using it as an electronic device, as time travels due to wear and tear and because of some environmental conditions, after some time it will tire out. So this is a major concern. So how do we constantly without changing any batteries rely on some other sources? Actually, lot of other alternate sources are there. Most of them are relying on solar power or wind power because they have a high density source. The solar power and wind power, they are high density sources. So Other than that, what else we can do? What else we can make use of to power these IoT related devices? That is a very big question. And this is at the heart of today's talk, actually, this question. And this is a very famous article based on that. So if you are seeing, all those such devices are using are mainly reliable on batteries, actually. So what is the environmental impact of these batteries, okay, after they worn out? That is a major thing. Making use of batteries for powering IoT is not a big thing. We can make use of it even if it is worn and torn. There are lots of exemptions. Like we can use like multiple number of batteries at a time, or with a small delay in between, we can replace the battery. Okay, so that is not the issue. But if we have a battery worn out, what will we do with this battery? That is a big question. So if we are coming to that, these IoT devices, most commonly batteries, when comes with its own challenges. Okay, so it frequently replaces require replacement, but this process is actually increasingly unsustainable. Okay, because the number of devices which is using this battery for powering that devices is like millions and trillions. So that is a problem there. So the demand for batteries to power IoT devices is actually a burden on our environment. That is a big thing. Okay, so if you are seeing the impact, like some of the what is that? Some of the articles, it's telling that over 3 million tons of batteries are actually discarded worldwide. This is a like tactics which we have got around 2024. Okay, so when the IoT devices, as I told in the previous slides, if it is going to be millions and trillions by 2050, then what will be the impact of this battery disposal to our environment? You can just think of. Okay, and you know that what is it because of? It is because of the toxic chemicals which is included in these batteries, which will destroy our ecosystem, including soil and other water systems. So if you're coming to any sustainable alternative for this, there is an alternative which is called energy harvesting. So I don't know how many of you will be working on this energy harvesting. It's a very famous application. So if there is energy harvesting, if there is energy existing in nature, then we can harvest that energy. What form of energy we can harvest? That is a question. Okay, so what are the possible sources of energy which which has high impact? Those are solar and wind, actually. Other than that, what else we can harvest energy from? What are the other sources which can harvest energy from? That is actually the question. So scientists were working on that, and they have found out so many other energies to be harvested, like vibrations, light, temperature fluctuations, and some other sources which are already existing in nature, and which is abundant in the form. So by harvesting this energy, we can power IoT devices without using batteries. So what it will do is it will reduce the weight and it will minimize the environmental pollution also. So that is one advantage. Okay, so if you are seeing energy harvesting technologies, one such technology which makes use of some type of conversion, which will convert this energy to a usable power, is by using piezoelectric transduction method. Okay, so most of them, if you have some mechanical also, electrical also, they might be knowing what is piezoelectric. So if you are seeing the existing potential of piezoelectric energy harvesting, I'm just coming to the topic of acoustic energy harvesting using piezoelectric transduction method. I'm just concentrating on piezoelectric based transduction methods. Transduction methods means how to convert this energy to usable voltage or current or usable power. So I'm just narrowing down to this particular topic, piezoelectric based transduction. Okay, so if you're seeing the existing potential of this piezoelectric energy harvesting, The piezoelectric effect. What is meant by piezoelectric effect? Most of them will be doing, like the piezoelectric materials which are readily available in nature. What they will do is, if they are mechanically getting strained, means it will produce a voltage or power by itself. Okay, it doesn't need an external power source. That is the biggest advantage if you are thinking about piezoelectric transduction methods. So it will generate an electrical charge in response to a mechanical stress. An example of a mechanical stress, most widely used mechanical stress is related to vibrations. So most of them will be dealing with the structures and all, so they might be knowing these things. So this principle actually allows us to capture the mechanical energy and other environmental sources, and it is converted to usable electrical energy actually. Okay, so piezoelectric energy harvesting, if you are like narrowing down, the most important application of piezoelectric energy harvesting is vibration energy harvesting. Okay, so what are the sources of vibration which are readily existing in nature? That is the next question. So if you are coming to the piezoelectric, if you are coming to the role of this piezoelectric materials in energy harvesting, there are different materials available, readily available materials and man-made materials also. Readily available, even we are having some piezoelectric materials with us, our bone, teeth, some hair strains, all these are having some piezoelectric properties with it by itself. Other than that, we have man-made materials also, like other natural materials also, piezoelectric materials readily available in nature. So how to make use of this material is the biggest challenge. And if you are making, what is the role of this material in energy harvesting? It's directly converting mechanical energy to electrical energy, and biggest advantage is it doesn't need an external power source. It is an active working material. It doesn't need an external power source. So it is sustainable and it is a renewable energy also. You know that this piezoelectric materials, it's readily available in nature. And one more important thing is that without using any other connection materials, we can integrate it with any of the existing structures. So it will not have any like major impact on these structures, because all the mechanical structures or like electronics related or electrical related structures, if you are seeing, it will be a little bit what is that, huge, right? Like mobile parts are there, means it will be huge. But if we are going for such materials, it need not be necessary that our piezoelectric material will, it will definitely integrate with that existing structures, but we can make use of that for energy harvesting or not. It depends upon the structure also. So we can easily integrate. That is a major thing. Okay, whether we can make use of this for energy harvesting or not, that is secondary. Now, another important factor is miniaturization and versatility. So it is converting the available source to the available power, to the power which we need, is by itself. We don't have to do anything. Even for man-made materials, okay, we have to go through some processes which will make it a piezoelectric material. But still, we have already existing standards for converting a material to a piezoelectric material. So after going through all those processes, it will have the versatility to convert a strain, mechanical strain, to the piezoelectric, to the power or voltage. And secondary thing is that if you are making use of a piezoelectric material, based on the type of piezoelectric materials which we are using, we can make it in different shapes and sizes. So if you are telling, as I told you, we started with IoT power, how to power an IoT devices. So all these energy harvesting techniques are actually looking forward to this IoT, the growth of these IoT devices only. And you know that most of the IoT devices are actually trying to minimize the structure of the sensors which they are using. Minimize in the sense, previously it was in micro size, now it is already come to nano size, and now it is going to the femto size. So miniaturization, so according to how the sensors is becoming miniaturized, this piezoelectric energy harvesting structures also have to become miniaturized. Okay, so this miniaturization and the piezoelectricity is working properly or not. So if we are coupling these two, then it will be having major applications in electronic side, also, in MEMS side also. So, and secondary thing is that we don't have to replace this thing. Of course, after some like time comes, it will wear out, but the wearing out is not as frequently as the battery. So we don't have to go for like, we don't have to think about the continuity of the energy which this piezoelectric material is supplying. It's compared to the batteries, we can tell that it is continuous energy supplying materials. And coming to the cost and energy efficiency, if you are comparing with the batteries, cost and energy efficiency are also high. And we don't need a maintenance for this thing because it is having piezoelectricity by itself. Okay, so these are some of the like major advantages of this piezoelectric material when we are using it in energy harvesting. There are so many other transduction principles which is being used other than piezoelectric transduction, electromechanical, then magnetic, electromagnetic. All these are other transduction methods which is being used. But piezoelectric transduction method is the most widely used because of these listed advantages. Okay, so these are some sources like or applications where we can make use of these piezoelectric, like buildings and bridges. If they are there, huge vibrations are actually coming out of these buildings and oscillations. So if we are making use of those vibrations, we can convert those vibrations. Actually, it is getting wasted. These vibrations are actually not being used anywhere, right? But it cannot be avoided also. If we have a building or bridge, these oscillations are already existing. We cannot remove those oscillations. So why can't we make use of such oscillations for powering some devices? It is actually some added advantage we can tell. And other than that, like when we are walking, when we are doing exercises, when a vehicle is moving, when all these actually produces vibration. So we can make use of these vibrations for converting to power using this piezoelectric transduction method. That is one major advantage. Now, if you're coming to health sector and like health sector, you know that they are doing most of this research based on how to improve the health sector. And they are making use of all the new technologies. So IoT technology is looking forward for the major applications in health and military actually. So if you're coming to health sector, we can make use of these vibrations because, so that it can be converted to useful power. But the question is how much power we can generate from these type of vibrations. If we have a building or if we have a vehicle travel, if we have a vehicle moving, all these vibrations will be huge, right? But if we are seeing the vibrations which are emerging from our body, from the human body, or from the body of animals, any movable object, if you are seeing the vibrations coming out of those body, it's very less actually. The strength of the vibration or the effect of that vibration will be very less. So the question arises there is like how much energy can be how much power can be generated from these vibrations. Okay, so there comes the importance of this piezoelectric type of transduction. So if you are going for other electromechanical or thermomechanical, electromechanical, thermoelectric, or electromagnetic transduction methods, actually they want huge vibration source actually, if you are seeing, and some of them want external power sources also. Like thermoelectric, if you are using, we should have a external power source. So in piezoelectric, all these conditions are not there. Okay, it doesn't need any external power source, and even if it is a small source of vibration, it can convert directly into useful power. Okay. So if you are seeing such a vibration, so many other vibrations are there readily available in nature due to water movement, due to air movement. All these are actually producing vibrations. So another such source of vibration is actually acoustic energy. You know that acoustic energy is everywhere, but still if it is a often overlooked source of power actually. Like very few, if you are referring to the research related to acoustic energy harvesting, very few papers are there. I can assure that less than 200 papers are there, which is making use of this acoustic energy harvesting, which is actually telling something about acoustic energy harvesting. Like it's being studied from like long before, but most of the researchers are actually getting output from recent years, like around 1990s or something like that. Still, we can tell that less than 200 or 250 papers are there where we can see this research related to the acoustic energy harvesting. So why is it so? Okay, so before getting into why is it so, I'll just tell what is acoustic energy harvesting. You know, acoustics is physics related to studies. So, sorry, physics related to sound. So, if you are seeing what is the definition of acoustic energy harvesting, it's converting a high and continuous acoustic source wave from an environment where it is readily available, where the acoustic source is readily available, into some useful power or electrical energy. It can be either voltage or current. Mostly it will be voltage only. And as I told you, like acoustic energy harvesting is not actually being used frequently for it's not actually being used for generating the power. But what is the reason for this? Okay, so as I told, if you are seeing the definition of this acoustic energy harvesting, I told the converting high and continuous acoustic waves from the environment where it is readily available into an electrical power. So high and continuous acoustic waves we should have. So when we are talking, for example, if you are seeing when a person is talking, we have acoustic energy, but is it continuous? When we are talking, it is there. When we are not talking, it is not there. But if you are seeing in one sense, suppose if we are there in an air chamber or acoustic chamber or something, acoustic chamber means where we are restricting these acoustic sources. Okay, we can tell that there is no acoustic sound inside. But if you are going outside, always everywhere sound will be there. Even if you are talking or some other person surrounding you are talking, always sound will be there. Even if two such persons are not talking also, from the environment, because of different various factors, the sound is actually coming. And that is one reason, okay, why we can make use of this energy. Now, second thing is that converting high and continuous acoustic waves. So it should be high. Okay, so so what will produce a high acoustic wave? That is a secondary thing. So it is always optional to have a large device. Okay, so there should be a large device. And if you are talking, the sound waves, I don't know how many of you know more about acoustics. Those who are working on acoustics knows that this acoustic energy, when it is getting generated from a source, it travels as a planar waves. It is actually from the source, it is actually getting distributed. It's not coming in a particular path or something like that to the destination. It's actually getting distracted in between. It's actually getting disturbed, and after that it is coming to the source. Okay, so if we want to harvest energy, maximum energy out of this acoustic source, acoustic sound, acoustic source, what we can do is we should have a efficient, large focusing device, which will actually take the sound from the source to the destination without any disturbance or without any loss, actually, we can do. Okay, so that is one thing. And other thing is that what is the energy source? How much is the energy source which we are getting from this sound energy? When we are talking, how much is the energy? What is the density of energy which is present in this sound source? It's very low, actually. Okay, if we are taking all the sound, I don't know how much you can understand. If you are taking all the sound of this universe, the power of that sound we can just confine to a glass, just a normal glass. That much only is the energy density of all the sound which is existing in the nature. Okay, so it's a very, very, very low power density source. But thing is that even if it is a low power density source, it's always there. Okay, it is getting wasted. So since it is getting wasted, why can't we make use of this energy which is getting wasted? And where do we use, even if we are making energy out of these sources, as I told you, since it is a very low power density source, whatever energy we are getting from this acoustic energy will be very less. Very, very less. So where can we use this energy? How will we power? As I told, we can power some devices, right? IoT devices. But which type of IoT devices we can power? So there comes the growth of this technology, MEMS technology, nanotechnology, femto technology. They are actually reducing the size of the sensors. So a small sensors, a MEMS sensors or a nano sensor, it needs just nanowatts of power to power for it to work. So this much power we can get from the acoustic energy. The only thing is that the energy density is very less from this source, but we can make use of it in some applications. Okay, so that is one thing. And second thing is that even if we are converting this energy to useful power, does it have any impact on the like impact of on the environment? Like as I told, IoT devices, they are making use of batteries nowadays. Batteries, after wearing out, what you will do with the batteries? How will you throw these batteries? When you're throwing a battery, actually it is having an environmental impact, right? It's actually destroying, it's actually polluting the environment a little bit at least. Now there are multiple sources, but still it's having some impact on it. So if you are making use of this energy, which is just getting wasted, as you know, even if energy, sound energy is getting produced, it doesn't have any economic or environmental impact in the energy system, right? Even if we are making use of it or not making use of it, it doesn't have any impact. But if you are making use of it, we have a lot of advantages also. We don't have any disadvantage. So that is where we make use of this acoustic energy harvesting tools. Okay, so for harvesting this energy from the acoustic source, we need actually some device which is called, which we will abbreviate from here onwards as AEH, acoustic energy harvesting device. So it will convert the wasted sound energy into some useful power by means of some, actually it needs a transduction method. Okay, so if you are seeing the acoustic energy harvesting, as I told, why acoustic energy harvesting? These are some of the sources of sound which is listed, and which is like compared to the other sources, as I told you, even if the energy density is very low for this power, these are some of the sources which can make use of for harvesting energy from. Okay, so these are having considerable energy density compared to the other sources of sound. Okay, anyway, it is all around us, and it is actually sometimes a nuisance. Not always, but it is actually a nuisance if it is continuous and a big source. Okay, so why can't we make use of it? And what it will do is it will reduce the nuisance also, and we'll get power out of it. That is advantage. Now, if you are coming to energy harvesting, as I told you, these all what is that, points I have already explained to you. Like it can be harvested without any negative impact to the environment. And why is it actually booming, this acoustic energy harvesting? It's due to the technological development in the area of MEMS, NEMS, MEMS in the sense micro mechanical devices and nano devices. And now it is actually coming to femto, where like you know that electric vehicles and all nowadays, research related to electric vehicles and all are booming. Actually, they are looking forward to some sources which is already existing in such type of electrical vehicles actually. So there we can make use of, because in electrical vehicles, you know that lot of motors and other things are there. And when motor is running, you know that like vibrations due to sound is of course there. So we can make use of those things to harvest energy from. So that is there. And where is it actually being used? This acoustic energy harvesting. As I told you, if you are seeing around us, we have this noise which is getting wasted. But other than that, if you are seeing, we have sunlight. Okay, from sunlight, due to photosynthesis, we'll get some energy. That is one form of energy harvesting. We can harvest energy. We have wind. We have what is that? Other vibrations. So then all these are existing together, where we will make use of the sound waves to harvest energy from. So where there is no structural path between the source and harvester. Okay, so in that case, this acoustic energy harvesting is the only source. Suppose if we are making use of wind energy, we need a windmill, right? And so such sources we need. Suppose if we don't have such sources and we have an existing application with us, all of us are using some existing applications like which is having nano, femto, all these devices inside, which is our mobile phone. It's always with us. Other than that, smartwatch, all the other things are there. So these are always actually, we are carrying these devices. In these devices, actually, we have structures which we can make use of for energy harvesting. We don't need an extra structural part for this. That is one advantage where we can make use of this acoustic energy. If we want to harvest energy from the windmill, we need a windmill, okay, which is exclusively for that particular application, for that particular condition. But in case of acoustic energy harvesting, when we are making use of, we just need some like we'll get into the details of that, then you will understand more. Like we need some structures which is already existing, which is being used for some other purposes. So what we are doing is we'll make use of the already existing structures to harvest energy from without interrupting its actual function. That is one major point which is to be noted. Okay. Now, these are some of the energy harvesting devices which is reported. So before coming into that, I'll just tell you what are the energy harvesting types. Then only you will understand those things. So if you're coming to different types of energy harvesters, acoustic energy harvesters, two major types of energy harvesters are there. Okay, one type is and most widely used type is the first one, which is using an acoustic resonator or an acoustic duct, we can tell. So most of the people who are related to this structures, they know what is an acoustic duct. Okay, and second one is making use of a special man-made arrangement which is called a sonic crystal. Okay, so if you are having, the first one is actually widely used if you are seeing acoustic energy harvesting devices. So it just needs a acoustic resonator. I told you. What is a resonator? Resonator is actually a duct. Okay, duct means it's a pipe-like thing which will allow, it's actually a waveguide. It will allow a wave to pass through it. So if it is an acoustic resonator, it allows the sound waves to pass through it without any what is that, loss actually. Okay, so and it will not allow the sound waves, it will allow the sound waves to pass through it without any loss. That is one advantage. Other than that, it will not have any impact on outside factors to this sound source. That is another advantage. Okay, so it's actually, a resonator is actually a means of eliminating undesirable components from the sound source. That is one thing. And other than that, another major advantage is it will actually amplify the sound waves. So as I told you, if we have a low power, even though the sound energy is whatever we are making use of is low power density source, we can amplify it to some extent using these ducts also. And you know that these acoustic resonators type or acoustic duct-like structures are there everywhere. It's just a tube or something like that. Okay, different acoustic resonators are there. So if we have such resonators, one simple such resonator is a tube-like thing. So if you have a tube-like thing, you can make use of that tube-like thing for harvesting acoustic energy. Okay, so that is first thing. Now, if you are coming to the second one, it's making use of a man-made material called a sonic crystal. Okay, sonic crystal is actually an acoustic metamaterial. It's a special type of arrangement where this tube-like structures made up of acrylic, usually it will be made up of acrylic. It will be actually arranged in a periodic manner. Okay, and where it will be arranged will be in a pool of fluid. Okay, so the fluid, don't think that we are immersing it in the fluid. There will be a pool of fluid in which it will be arranged in a periodic manner. Why we are arranging it in a fluid is when there is a movement of fluid, there will be acoustic waves trapped inside these tubes. How it is getting trapped inside the tube is, suppose if you are that tube is actually working as a resonator. Okay, so if you are seeing, just take an example of a simple way to explain a resonator is our water bottles. Okay, just empty a water bottle, just open the water bottle, so the mouth of the bottle will be open, and you just blow over, or you make a sound over the top or the opening of the water bottle. You can hear some sound, or if you are just blowing air over the surface of that opened surface, you can hear some sound from the bottle. So that is due to something called resonance, which you might be aware of. Okay, so these sonic crystals are also making use of these things. So when we are immersing it in water, you can see this arrangement here. I hope everybody is able to see this. Like in the sonic crystal, you can see that some tubes are arranged, and underneath the tubes there are some water pool. Okay, fluid pool. And that fluid can be water or oil or any such special viscous materials or specially viscous fluids. Okay, so what it will do is when sound is actually passed over the surface of these tubes, it will trap acoustic energy or sound energy in between these tubes. Okay, so that is what actually it is making use of. This sonic crystals is making use of. So actually it's trapping the sound. Okay, so by using by controlling the number of tubes and by controlling the amount of fluid in which it is immersed, we can control and we can manipulate the sound waves. How much we need the sound, how much sound should be created due to this arrangement, we can control that by controlling the number of tubes and also the amount of liquid which we are immersing these tubes. Okay, so these are the two types of acoustic energy harvesting devices which will make use of for acoustic energy harvesting. So I will be concentrating more on this acoustic energy harvesters, which is using acoustic resonators. Okay, now we have these acoustic resonators or sonic crystals for trapping the sound or to get the sound which is actually getting wasted. Okay, now how to convert? Question is how to convert this into useful power. Okay, so in that case, if you are seeing, we have, as I told before, we can make use of different transduction methods. So two important types of transduction methods actually we are making use of: piezoelectric and electromagnetic. Okay, there is another transduction method which is not purely acoustic, but it is related to acoustic. There are actually two transduction methods in thermoacoustics. Temperature is actually converted to acoustic energy, and that acoustic energy we can harvest through some other transduction methods. Okay, so there are two types of conversions are actually happening. That's why I didn't listed it here in this. This is based on pure acoustic conversion. Okay, so mainly we'll make use of piezoelectric and electromagnetic. We'll not make use of other transduction methods. Why? I'll explain it after some time. Okay, so in that, piezoelectric is the most widely used because of the advantages which I have listed before. Okay, all those advantages are applicable in vibration energy harvesting also, here also. The major thing, if you are seeing related to piezoelectric transduction method being used for acoustic energy harvesting is, it can be reduced into any miniaturized size. Okay, so because acoustic energy harvesting will generate very less power, which we can make use of to power MEMS or NEMS devices only. So the transduction methods which transduction structures which we are making use of should be very small. So in that case, piezoelectric material we can miniaturize, we can made it into any small size. So that is one major advantage. Now, if you are seeing electromagnetic, sometimes we need some external power sources for electromagnetic. Definitely it will, but there should be some arrangement for this electromagnetic to work. Sometimes in all the cases it might not work, but piezoelectric we can just make use of, because it is an inbuilt property in it. Okay, so we just need to paste it somewhere, or we just need to insert it somewhere along with the duct, so it will just work. So that is one major advantage. So I'll be concentrating mostly on acoustic resonator based energy harvesters, acoustic energy harvesters, which is making use of this piezoelectric transduction methods. Okay, so I hope you all are getting this. And if you are coming to this acoustic energy harvesting devices, which is reported, no, there is a paper which is written, which is based on the review of these acoustic energy harvesters. Okay, when I was doing PhD, there was hardly 10 to 15 papers which I should refer for this acoustic energy harvesters. So there is a review paper based on this. If you are interested, you can go. This is a first reference. Just when I'm listing out the reference, you can note down if you want. So this is one thing. Now, if you are seeing the first figure is based on a resonator, which is called a Helmholtz resonator. If you are seeing the shape of that resonator, it has some cavity and an opening. It's just like a water bottle, which is having a different shape. Okay, so we can make use of the transduction method. Here in the first figure, it is making use of electromagnetic transduction. Second figure, that is also making use of electromagnetic transduction. You can see this thing. So both are making use of some type of ducts, and at the end of the duct we have a transduction method, okay, which is electromagnetic. If you're seeing the third figure, you can see that this sonic crystals are being used. Okay, so sonic crystals are being used, and inside the sonic crystals, as I told you, sonic crystals, it is an arrangement of tubes which is inserted, immersed in a fluid. So if you're seeing, this is a region which is in between these tubes. Okay, this is an expanded image of the region which is in between the tubes. If you're seeing the region, the sound waves will be trapped in this region. Okay, due to the sonic crystals, due to the normal working of the sonic crystal. And if you are making use of the transduction element there, which is a piezoelectric material, as I told you, piezoelectric transduction element, if you are making use of, you just have to insert it there. That's all. We don't have to do anything, any type of arrangements there. We don't need an extra structure there. So we can just insert it there. So what it will do is it will convert, since it has the power of converting the mechanicals. Due to this sound energy, this particular piezoelectric transduction element will get strained and will get a corresponding voltage. Okay, so that is one thing. So the fourth figure, if you are seeing, this is just one device which is making use of an energy harvesting material, energy harvesting structure inside it to harvest energy. This is actually being used for military purposes. This structure is actually being used for military purposes in underwater applications. So this structure, you can see, if you are seeing, you can see that a duct-like structure is already there. Okay, so they are making use of this in military application. So we can make use of this structure without actually affecting its actual functioning. Actual functioning, as I told you, will be inserted in some sonar devices, actually military sonar devices. Since it has a duct-like structure already in it, what we can do is we can insert a transduction method inside, such that just like that we cannot insert a transduction what is a piezoelectric transducer inside. We can introduce a transducer inside such that it will not affect the normal working of this particular structure. Okay, so it's a real-time image. Now, if you are coming to these images, if you are seeing, see the last one is again making use of a duct. Last one, you can see a neck cavity. It's a Helmholtz resonator. Actually, it's a duct-like thing. So it's making use of a piezoelectric material as a membrane at the closed end of it. Okay, so as I told you, if you are seeing this figure, you may not be feeling like it is so simple that we have to just insert, we have to just change the backside of this duct with a membrane, piezoelectric membrane, then it will work. It's not like that. When we are changing the backplate of this resonator with a piezoelectric material, the actual working of that duct will change. Okay, so it should not happen. So we have to make the structure such that it will not affect the actual functioning of that duct. That is also there. And if you are seeing the first figure, that is a simulation figure actually. This has been simulated in ANSYS actually. In this figure, you can see a long tube. It's a duct. It's a type of duct. So I'll come to the different types of duct actually. This is a type of duct which is called a quarter wave length duct. So you can just insert piezoelectric cantilever beams inside. What is a cantilever beam? You all might be aware of. Anything which is fixed at one end, the other end, if it is free, it's called a cantilever structure. So in this tube actually, they have inserted so many small piezoelectric cantilever beams. If one end of this duct will be open, so if you have a sound source at the end, what the duct will do is it will amplify the sound inside, and that sound inside will strain this piezoelectric material to produce some energy. Okay, now this is a simulated version of that, meshed version of that, this particular figure. Okay, so if you are coming to why do we need the duct resonators? As I told you, it amplifies the sound like which is already there existing, because we need already the sound is a low power density source. So as much as we can amplify, it's good. That much high power we can generate. Okay, so that is one thing. Other than that, as I told you, sound waves are actually traveling as planar waves. It's on the way when we are producing a sound, when it is traveling from the source to the destination, on the way actually it is getting diffracted. Okay, lot of interferences are there due to external interferences also. Just like that in medium, if sound wave is traveling, it is actually getting distracted. Lots of energy from the sound wave is actually getting wasted. Okay, it's actually getting lost actually. So without any loss, if we want to effectively transmit the sound waves to the transduction element actually here is a piezoelectric material. Okay, so without any loss, if we want to make use of this sound so that it will strain the piezoelectric material, we need a what is that? We need a path. Okay, so that path we can assume to be this duct. So that will amplify the sound on the way, it will amplify the sound which it is carrying, and along with that, it will effectively transmit the sound to the transduction element without much loss. But there will be loss, we cannot reduce that thing. You know, like most of you might be knowing about acoustics, very complicated physics, which we cannot control like too much. Okay, however we are controlling, there will be, of course, losses, and losses will be there due to different factors, which is not under our control. Okay. Now, if you are seeing the different types of ducts, as I told you, which is frequently being used for acoustic energy harvesters. If you are seeing one such resonator, Helmholtz resonator, Another resonator is this like quarter wavelength resonators. Okay, so it can be quarter wavelength resonator or half wavelength resonator. So all these, as I told you, are resonators. Duct means acoustic duct only. It's resonator. So it's it works on resonance. What is resonance? Resonance is actually a condition where we'll get whatever it's carrying, whatever energy or whatever value it is carrying, it will be high at a particular frequency. Okay, that is what is called resonator. So resonance is actually a condition which will give you a high impact, high output at a particular frequency that is there. So if a resonator is there, it will give you, if it is a acoustic resonator, what it will do is the sound it will carry, it will have different resonant modes or resonant frequencies. So at one particular frequency, this sound wave will have highest amplitude. Okay, so that is there. So all these, as I told you, most of the energy harvesting devices, if you are seeing, most of them are actually based on the condition, this resonance condition. Okay, so acoustic energy harvesting also is making use of this resonance. Even if it is a sonic crystal also, it is making use of resonance only. Okay, so Helmholtz resonator, you can just imagine Helmholtz resonator as something which is having a neck and a cavity, something like our bottle, water bottle. So water bottle, if you are seeing, the place where we are like using it for drinking, no, that place we can call it as the neck of the water bottle, and the water is filled somewhere, that is actually the cavity of that particular bottle. Okay, so you can imagine Helmholtz resonator as, say, water bottle. And other resonators are quarter wavelength resonators and half wavelength resonators. Why we are telling about the wavelength is, as I told you, these resonators are all based on this resonance condition, which is based on a one particular frequency. So you know that something which is having a resonator and a source which will have a particular wavelength associated with it, right? So half wavelength resonator, the wavelength of the sound which is traveling inside will be half of the wavelength of the sound which is at the entrance or at the source. So half of the wavelength of the source sound. Okay, so you can imagine half wavelength resonator as a tube which is opened at both ends. Okay, now if you are seeing a quarter wavelength resonator, it is just like a tube which is opened at one end and closed at the other end. So what is a why its name is like that is, if you are seeing the wavelength of the sound which is getting trapped inside will be quarter, like 1/4 of the wavelength of the sound, which is wavelength of the actual sound actually. Okay, so that is there. So these are the different resonators which is making use of. These are the basic structures. Okay, the basic structures of these resonators. So Helmholtz resonator, if you are seeing, it should have a cavity and a neck. Okay, so based on how you are changing the structure of these resonators, you can change the amount of sound which is trapped inside. Okay, so if you are designing an acoustic energy harvester, two things are there. There is a duct and there is a transduction material or a piezoelectric transduction structure. Okay, other than that, we have a resonance structure in which we will insert the piezoelectric transduction. So if we want to design an acoustic energy harvester, we can make changes, or we can do research according to two different perspectives. One is whether we can change the structure of this duct without altering its actual function, so that it will increase, it will actually increase the actual what is that actual working of this particular structure in energy harvesting. What is the actual working of this structure in energy harvesting? It is actually amplifying the sound waves which is getting trapped inside, and it is effectively transmitting the sound from the source to the transduction unit. So if we are altering this structure, whether we can get it, those things modified. Okay, that is one thing. Now, second thing is that, can we change the structure of the transduction material. Piezoelectric material is there. So coming to different piezoelectric materials, after coming to different piezoelectric material, I'll just go through the structural changes in piezoelectric material. Okay. Now, as I told you, why piezoelectric transduction is used for acoustic energy harvesting is due to the direct and easy attachment to these resonator structures. We don't need an extra something to attach this inside the resonator structures. We can just make use of a normal soldering or something like that. Okay, so if you're coming to different types of piezoelectric materials which is being used, two different materials are there. One is PVDF films and the second one is piezoelectrics. Okay, so recent research on acoustic energy harvesting is actually concentrating on these PVDF films. PVDF films are you can see the figure. You can see that it's very thin and it is made up of a flexible material. PVDF is polyvinylidene difluoride films. Okay, it's a film. Film means it is very flexible, right? Second thing is piezoelectric strips. Okay, piezoelectric strips, as in if you're seeing the figure, you can see that it's little brittle compared to this flexible PVDF films. Okay, so PVDF films have the highest advantage of these flexible. These PVDF films are, it's very flexible. So there comes the importance of acoustic energy harvesting. See, this acoustic energy is a very low power density source. So when very low strength sound energy is actually used to what is that? Mechanically strain this PVDF films, right? So it will be, if it is very flexible, then it is very easy to get strained. So there comes this PVDF, importance of this PVDF films. Okay, but if you are seeing this piezoelectric strips, it is just brittle, a little bit brittle compared to that of PVDF films. Brittle in the sense it's something like a biscuit, not too strong, something like a biscuit. If you are applying more stress, it will break. That is there. But from acoustic energy, we won't get that much more stress. Okay. So thing is that it is very difficult to strain this piezoelectric strips by using acoustic energy harvesting. But there are some piezoelectric strips which are available, readily available in market now, which we can make use of to strain this piezoelectric strips, because the strips are very thin nowadays. We can make use of such strips compound strips are there which we can make use of. But if you're seeing the PVDF films, it's something like a plastic, you can tell. It's very flexible. But the disadvantage, and it has, since it is flexible and made up of plastic, you can, plastic, it's not actually plastic, something similar to a plastic. Okay, not very, what to tell, not as dangerous as plastic. Okay, so since it is similar to plastic, you can imagine the chemical resistance of these type of PVDF films. Okay, so you can use it in any harsh environment also. But if you are seeing these piezoelectric strips, as I told you, it's fragile, it's little brittle. So if you are using it in harsh environments, it may break. That is there. So, but the thing is that piezoelectric strips are actually good in conversion of any mechanical strain to electrical output. Okay, why is it so? It's these piezoelectric materials are having different characteristics. Okay, one such characteristic is one such parameter is which is deciding its piezoelectricity is electromechanical coupling coefficient. Electromechanical coupling coefficient is a parameter which will tell us how much electrical energy, how much mechanical energy can be converted to electrical energy. Okay, so this coupling coefficient is high for piezoelectric strips. That means even if it is a small strength source, it will strain the piezoelectric material, and you will get, since this coupling coefficient is very high, you will get a high voltage. Same time, if you are seeing the PVDF films, this electromechanical coupling coefficient is very low. Okay, even though flexibility is there, if you are seeing low strength mechanical source also can strain this PVDF films. But the thing is that even though low mechanical source is straining this PVDF films, the amount of energy conversion is less compared to that of PZT steps. Suppose if you are using same amount of mechanical energy to strain this PZT and PVDA films with same thickness, then PZT strips will give you high voltage. That is there. But always we cannot make use of PZT strips. In harsh environments, we cannot make use of PZT strips. There we can make use of PVDF only. Even though the energy conversion is not good, we'll get some energy from that, right? But we cannot make use of PZT strips as it may break. It's very fragile. That is there. Okay. Hope you are getting this. So if you are seeing, these two are the different duct resonators, and this PZT or piezoelectric transduction elements are the major component of these energy harvesting devices. So, research perspective, if we are seeing, we can alter the structure of both so that we can increase the harvested power. Okay, so that is there. Now, if you are seeing the basic concept of energy harvesting, as I told you, there will be a sound source, whatever is it. We'll use a plane wave tube or an acoustic resonator. So we can make use of energy harvester or the transduction element anywhere inside the duct. Okay. So research perspective, if you are seeing, not only altering the structure of the duct or piezoelectric energy harvesting, another major research problem is where to place this piezoelectric material. Okay, inside the duct or backside of the duct or outside of the duct or at the entrance of the duct, where to place it and how to place it. Can we use it in a cantilever beam form? There are some other structural forms also. Fixed beams are there. Fixed free beams are there. Pinned beams are there. We can make use of these piezoelectric transduction elements in any of these structural forms. So, in which structural form we should place this, inside the duct or where to place? That is another research concept. And as I told you, the power which is harvested is very less, so we need a power management circuitry. That is another research area, very huge research area actually. It is how to make an efficient structure, like miniaturize the size so that it will amplify the harvested power. Okay. Now, these are some of the works which I have conducted. Okay, so if you are seeing the acoustic energy harvesters using Helmholtz resonator, I just started with a simple structure. So any resonator we can make use of, any material we can make use of, glass, aluminum or something like that. But usually we'll choose a material which is actually taking or which will make less loss of sound. Okay, so I have used an acrylic material to make use of this acoustic energy acoustic resonator actually. Acrylic material, and at the back side I need to control the length of the cavity of this resonator. You can see that in this figure, you can see that there is a tapered neck here. Okay, usually if you are seeing a bottle, if you are seeing this Helmholtz resonator basic structure, if you are seeing, just see the neck is straight neck, but just see here I have tapered. I didn't use a straight neck. I just tapered. I just bring a tapering to this neck. So what it does is it actually helped me to increase the sound which is trapped inside. Why is it? Why is the tapering affecting the sound increase? Is based on the resonance of this duct actually. Resonance of this duct actually is affected by the length of the neck, diameter of the neck, and the volume inside the cavity. Okay, volume inside the cavity. So when I changed the neck from straight to this tapered, not length actually, length, area, and volume of the cavity. So when I changed the neck from straight to this tapered end, what happens is the area got increased. Okay, so it increased the source which is actually trapped, sound source which is sound energy which is trapped inside. So I got a little bit amplification. So the sound energy normal piezoelectric convention happens actually. And now that was actually my first work, like starting work actually. Okay, whether any change, structural change, what I can do with to make the harvested to make maximum harvested energy out of these structures. So that is there. Now, another advantage, another change, as I told, is like whether I can change the structure of the piezoelectric transduction, which is whether it is having an impact. These are all studies, like studies which are done to confirm whether these structural changes are affecting the energy harvested or not. Okay, so like normal, due to tapering, I told you that the amount of energy, the sound energy trapped inside the duct will be high. So at the same place, what I did is like instead of using a cantilever beam based piezoelectric energy harvesting, I just added a mass to the cantilever beam. So like most of the structural engineers, you might be knowing that if you are adding a mass to the free end of the cantilever beam, it actually strains the cantilever beam more. Okay, so due to this straining, what happens is already the source power has increased, sound source has increased. So the mechanical strain which is being applied to the transduction element, it was increased, and I got an output. And now what is the, like, I didn't just add a end mass. Okay, usually when we are adding an end mass, it will be of regular size, like it will not be of irregular shape. Irregular shape in the sense, the area wise, if you're seeing, it will be of flat surface or constant area, something like that. Usually we'll add circular or square shape or something like that. But here I added a triangular shaped end mass. So what it will, and the advantage is that the end mass is also flexible. Not only the piezoelectric transduction element, the end mass, usually when you are adding mass will be made up of some hard material. It will not be flexible material. Okay, but here the mass is also flexible. So what will happen is the mass is flexible. So when vibration energy or sound related vibrations are hitting this transduction element, the mass will be strained. So that strain will affect the piezoelectric cantilever beam, and other than that, directly the sound waves will go and hit the piezoelectric beam. Because of that also, we'll have a piezoelectric strain. So the piezoelectric material cantilever is actually undergoing two types of forces actually, which is making it to get strained. One is the bending force, and another one is due to the bending of this mass, it will get twisted. So there is a concurrent bending and twisting force which is being applied to the cantilever beam so that it will get straight. So that is actually a structural modification of this, what is that? This particular AEH. So that was also working actually. It gave more energy compared to now. So that was working. So I just focused on this acoustic duct related energy harvesting devices. Okay, why I have concentrated most on acoustic duct related structural modification is, see, in piezoelectric material, when we are used inside, like how to test it is a big issue. Okay, usually these type of devices, these type of structures we can make use of in underwater sensors. Underwater sensors are having mostly these type of structures. Okay, glass related, tube related structures are there. There, if we are making use of this structural modifications of piezoelectric material, it won't affect that much due to the low SNR ratio there actually. Okay, due to the low SNR, underwater the SNR ratio, signal to noise ratio, is very less. That means the signal strength is very less compared to that of the noise. So their structural modifications of the piezoelectric material, it won't affect that much. As I told you, like here two experiments have been done. Okay, so the structural modification of the duct actually is producing more increase in output than the structural modification. Of course, structural modification of transduction element is maximizing the sound, but that increase is not that much effective. So I just concentrated on the structural modification of the duct. Okay, now if you are seeing these type of ducts, see, all these ducts are circular in nature, or conical ducts are actually there. Okay, so if you are seeing conical ducts, how will you create this conical duct? That is a big issue actually. If you are seeing sensors and all, of course, sensors and all are using these type of structures, but like, it's not as easy to make these type of conical structures. Even if it is there, sensors are using, underwater sensors are using, like sonar and all other things, no, they are using these type of structures. It's made up of some material, stainless steel, aluminum, or something like that. Okay, so this stainless steel related ducts is having some problems with it. Like why they are using this stainless steel and other materials are underwater. When they are using, they have to resist corrosion and all those things. So they have some particular materials being used. So making these type of structures underwater is for precise sensing applications. But if you are seeing some other structures where we can insert these type of piezoelectric materials quickly or without any like effect on the particular duct, actual working of the duct is rectangular shaped duct. And you know that it is very easy to make a rectangular shaped duct than a conical shaped duct. Conical shaped duct is having some curved structures, and making a duct means it's not so simple like just a tube or something like that. Okay, the dimensions of the tube, the radius of the tube, all these are actually affecting the working of the tube. So it's very difficult to make such type of ducts. And even if there is a duct, conical duct structure, if you are inserting the piezoelectric material inside the duct, it will change the acoustic property of that duct. It should not happen. Actually, it is being used for some other purpose. So it should not affect the actual functionality of that particular duct, right? So the one such thing is, if we are making use of rectangular duct, we can solve this issue. Okay, so there is a paper related to this acoustic rectangular duct. So in that study, I have concluded that even if we are using a rectangular or conical duct, the area of the cross-sectional area of that particular duct is not going to affect the function of that particular duct. Okay, so if you are seeing a rectangular duct, the cross-sectional area is cross-section is actually a rectangle. If you are seeing a conical duct, the cross-section is actually a circle. Okay, so this cross-section is not affecting the actual working of that duct. Okay, why is it so? Is it actually depends on, as I told you, the resonant property of this duct actually depends on, if it is a Helmholtz resonator, we have a neck and a cavity. So it depends upon the length of the neck, area of the neck, and the cavity, volume of the cavity. Okay, so if it is a this quarter wavelength, or if it is a quarter wavelength or a half wavelength resonator, it's just the what is that? This length which is affecting the wavelength and the particular frequency. Okay, nothing else. This area of cross section is not affecting the particular working of that particular resonator. That is because this wavelength is affected by the length, and because wavelength is affected by the length, it depends upon the sound. What is it? Sound velocity alone. Okay, velocity and wavelength will give you the frequency. So sound velocity is always constant. So wavelength is affected by the length. That means the frequency is affected by the length only. It doesn't have any impact on the area. So if you are coming to rectangular or if you are coming to rectangular duct or circular duct, the area when it is changing, it won't affect the duct. And suppose if you are making a tapering inside this duct, instead of making a straight tube, if you are making a tapering inside the duct, of course it will amplify the sound waves getting trapped inside, because the sound waves, the amplification of the sound waves depends upon the resonance, and the resonance depends upon the what is that, cavity also, cavity of that particular, and length of the duct also, and the cavity of the duct also. Okay, so when what is that, area of cross section, as I told you, area of cross section does not affect, but the total area or the volume, not area actually, the volume of the duct actually. So when we are tapering the duct, it actually increases the volume, right? And that is the reason why a structural modification of the duct I concentrated on. And one more thing is that if you're changing this area from area of cross section from conical to, if you're seeing the conical duct and rectangular duct, it's very easy to fabricate a rectangular duct. Just take 4 different sheets, or how many sides? 6 different sheets. Just screw it up to get the rectangular duct. But if it is a conical duct, we should make use of the like the curve of that particular conical duct. Actually, it matters. Okay, so easy manufacturer easiness. Manufacturing easiness is one major thing that I went to this rectangular duct. And thing is that this area of cross section, if it is changing, it won't affect the actual working of that particular duct in this application. Acoustic energy harvesting application also, in normal acoustic, other functions of this duct also. Okay, that is one study which is being done in acoustics. Okay, so this duct is having another structural modification, which is I have added a flange to the duct. Okay, flange is something like, if we are taking a bottle, the end of the bottle, the opening of the bottle is just like, it's not straight actually. Some small tapering like thing is there. Okay, so that is called a flange actually. At the mouth, there is a small tapering. That is called actually a flange. So if I have added a flange such that the size of the flange is very big. Okay, so if you are adding a flange like thing like that, the flange actually will prevent the sound waves to getting affected the sides of this duct. That is one thing. Acoustic resonator means it is actually working on acoustic sound waves alone. Okay, if the sound waves is going and hitting the sides of the duct, it may interrupt the other functionality, not acoustic energy harvesting functionality. This actual duct is being used for some other military applications, right? So because of this duct properties only, they are making use of this duct for that particular application. So when the sound waves in the sense, when we are telling sound waves, you should think about the actual real-time application. Suppose if it is a sonar, how much sound is actually getting created from the sonar. Okay, that sound is having some strong vibrations in it. So that vibration should not go and affect it. It should be at the mouth alone. It should not be on the sides of the duct, because it will affect the actual working of the duct. So for that, usually these duct-like structures, they will add a flange at the mouth of the duct. So the size of the flange will be chosen such that this flange will prevent the sound waves to go and affect the sides of the duct. So it will be little bit huge compared to that of the duct. See, this is this duct actually has been not only the duct, the whole setup along with the transduction element. Actually, I have inserted the piezoelectric transduction element at the back side of this duct. Okay, so the back plate of this duct actually. So the whole setup has been tested in the acoustic room or the acoustic chamber inside the NPOL lab actually. NPOL is Naval Physical Oceanographic Laboratory, which is there in Kochi. It's a military based DRDO lab actually, military DRDO lab, where underwater related works are going in. Actually, Navy related, all the Navy related works are they are being conducted in their DRDO lab. So this has been tested in their acoustic chamber. So why I did it in acoustic chamber is no other sound should interrupt it. Okay, first it should be tested like that. Then we should test it in real time environment. Okay, if it is working properly, then only we can study the effect of other sources on this particular duct other than energy harvesting. Whether it is properly harvesting energy or not, first we need to. For that, we should like block all the other acoustic sources, which can be done only in acoustic chambers. If you are, then I have tested it in real time also, and studied how much impact is there from other sources, which we cannot avoid. Okay, so whether it is decreasing, minimizing, maximizing the quantity of energy which is being harvested out. So this is a setup for that. So you can see in this figure that the flange is a little bit bigger than the duct. If you are seeing the duct, the size of the duct is smaller, and the flange is. And then you will be thinking that, okay, these type of structures are very, very big in size. Then how can we make use of this in MEMS or nano devices? Okay, so there are some scaling rules. As you all know, there are some scaling rules for nano and micro devices. So based on the scaling rules, we can scale these structures into smaller sizes. Okay, so I haven't worked on that. Like some of the people in POL are actually working on that. It's a major research area actually, how to scale these type of structures to nano scale. Actually, they haven't worked on this micro related, nano scale actually. Okay, and inside the acoustic chamber also, there are some sources which we cannot avoid. We have some hard things, right? Like we have to place this duct on a table. We should not place this on the what is that, on the floor, because floor is having it's having some vibration. And when we are I have tested it with the speaker. So when the speaker is on, it will produce some vibrations on the floor, which will be transferred through this duct through the table. Okay, through the floor, from the floor to the table, and through the table to the duct. So in order to avoid that, we have used some foam like thing which will prevent the vibrations, other vibrations. So all these have been tested, and if you are seeing the acoustic energy harvesting, one of the major areas where we can work more on is if we are placing the transduction element inside this. If we are just testing this duct, it will have some properties. But when we are placing the transduction element inside the duct, it will change the. It is actually causing a resonant shift. Okay, resonant frequency shift of the resonator. This resonator is actually having a resonant frequency, and the piezoelectric material is also having a resonant frequency. So we have to make this structure so that these two resonant frequencies are same. So when these two resonant frequencies are same, at that particular resonant frequency, we will get the highest energy, highest power harvested. So if you are seeing this highest power, when we are placing this piezoelectric material inside this duct, what will happen to the duct is its resonant frequency is actually getting shifted. It may increase or decrease, but definitely it's not the same resonant frequency, because the resonant frequency depends upon the dimensions of the duct. Once the dimensions of the duct is made, it's constant. We cannot change it, right? So what is happening is it's getting shifted when we are inserting the piezoelectric material. This is due to elastomechanical coupling inside this duct. When we are inserting some elastic material inside the duct, it's actually changing the coupling of these two things. So that is a very big research area where the MPOL is currently working on. So that is there. So these are some of the challenges I have told you. There are some other major challenges where research is actually concentrating in acoustic energy harvesters, in the design of acoustic energy harvesters. One is this low power source, energy source. So how to improve the sensitivity of the piezoelectric material? We cannot increase the density of acoustic energy, right? Because it's naturally created. So the thing is that from this low energy source, how can we get maximum energy? So that can be done by improving the, making some structural modification so that it will increase the sensitivity of that transduction element. That is one major area. Second thing is, as I told you, when you are inserting a piezoelectric material inside the duct, it is actually changing the resonant frequency of the duct. So how this change can be studied? That is another major research area. Now, with all these things incorporated, how can you miniaturize this? That is another thing. Acoustics is not so easy, very complicated physics actually. So how to make it into a small device? Okay, so if we can make a small device, acoustic energy harvester out of this, harvesting device out of this, it's a huge, what is that? What should I tell? Complement or achievement in the IoT related areas. Okay, so there are some tools which we'll make use of for this modeling of this acoustic related structures, acoustic energy harvesting structures. Simulation and modeling used to tools for this both ducts and resonators and transduction elements are, we need FEM softwares. Okay, those who are working with structures, they might be knowing. If you want to design something, if we are making use of FEM, finite element method, we can divide that structure into finite number of elements, and then we can analyze each of these elements, and the results of each of these small elements we can compare to get the actual result of the actual whole structure. So that is being done in FEM. So this can be this modeling, this structural related modeling, simulation modeling, we can make use of this FEM related software. So some such softwares are COMSOL, Multiphysics, ANSYS, MATLAB, all these things. Okay, and MATLAB is not an FEM software. Only COMSOL and ANSYS is FEM software. MATLAB is being used for other analysis. Okay, and when we are making use of this, these are using multi-physics, not only acoustic physics, it needs a piezoelectric related physics, acoustic physics, then frequency related physics, all these should be combined together. So we need multi-physics simulation in it. And if we need to, if after getting the output, after getting the generated power, also we can amplify the power. So for that we need an external signal conditioning unit, right? So that signal conditioning circuit is another research area, how to reduce that and how to get maximum power, how to maximize the harvested power. So there we can make use of circuit simulation softwares, like normal circuit simulation software, MT-SPICE and P-SPICE. So these are some of the applications where we can make use of these acoustic energy harvesters, like ultrasonic related applications we can make use of, because ultrasonic energy also we can make use of. Another thing is medical related applications. Now also, like one example I'll tell you is, heart is beating continuously, right? When a person is alive, his heart is beating continuously. That is a sound wave actually. That is producing some vibration. You know how much it is beating, right? Very low power density source, but that much power is actually we can make use of to power a pacemaker. Pacemakers, it's coming in very miniaturized size nowadays. So that is enough to make use of to power a pacemaker. That is one such application. So many such applications are actually being done, and people are working on how to make use of these brain waves and all. The vibrations from the brain waves and to convert it to useful something, headband or something we can make use of for harvesting power. Okay, and consumer electronics, you know that mobile phones, like millions and trillions of MEMS devices or nano devices are there. So if we have accelerometers, like accelerometers and all, we can make use of those structures. So we can add something to make use of those structures to harvest energy. So these are some of the examples where we can. And another thing is, I forgot to add this thing, military applications. So many military applications are actually working on how to make use of acoustic energy, because all the military applications based structures or military applications are using huge structures, right? So they are having mobile parts in it, which is producing sound energy. So how to make use of that thing is also there. And automotive and aircraft applications are also using this acoustic. They are working on it actually. In aeroplanes and all, if you're seeing both sides of the wing, you have a duct-like structure. So how to make use of it. But these duct-like structures, when we are using it in an aeroplane, it is in harsh environment. When it is flying, actually, it is in very harsh environment. It's working in very harsh environment. So when we are making use of those structures for acoustic energy harvesting, those transduction elements should be taken care of. So that is there. So these are some of the research and developments, okay, which I have been working on: acoustic energy harvesting using duct resonators and various transduction methods. Then underwater acoustic energy harvesting using duct resonators or piezoelectric transducers. Underwater, whatever we have done in air acoustics won't work for underwater, because in underwater, very like SNR ratio is very low. So that is there. Now, some other area also I'm working, wideband acoustic beamforming and all, acoustic source localization actually we can tell. And piezoelectric energy harvesters also, general vibration energy harvesters also. So actually I belongs to a specific research group in IIIT Kottayam, which is called I2CS, Intelligent Integrated Circuits and Systems Research Group. So these are the broad areas in which we are working on design of VLSI systems, instrumentation, and signal processing. So these are the references. So I'll be happy to answer any questions related to this.
If anyone have any questions? Ma'am, can you please explain the piezoelectric parameters that is incorporated with acoustic energy harvesting system?
Sir, all the piezoelectric. Yes.
Except coupling coefficient.
Sir, all those piezoelectric coefficients which is being used, strain constant, charge constant, voltage constants, all these parameters which is being made use of in vibration energy harvesting is actually affecting this.
Oh.
Because this sound energy harvesting means actually the vibrations related to sound. Because of sound, there will be some vibration, right? Sound means air particles vibration only.
Yes, yes.
So there's all those parameters which are being used for piezoelectric energy harvesters that will affect this acoustic energy harvesting also in a huge way, because the energy power source is, energy density of the source is very less. And it will have a huge impact actually. In vibration energy, it will not have that much impact. Like change will be less. But here it will be having a huge impact for each parameter.
Okay. If anybody have any questions? No, ma'am. There was a phenomenal speech by Dr. Minu Pillai on account of acoustic energy harvesting. Thank you, ma'am, for being so eloquent on the topic energy harvesting.
Thank you, sir. Thank you so much for this opportunity.
Thank you, teacher.